So here we discuss whirling of shafts. So in the left there is a vertical shaft and a disc is mounted on it. Here the horizontal shaft and a disc is mounted on it. So here the disc is not rotating. So in this condition the disc is not rotating. So the shaft coincides with the axis of rotation. So here also the shaft coincides with the axis of rotation. Shaft is undeformed and it coincides with the axis of rotation. But here what happens in both of these cases, due to some manufacturing inaccuracies or due to some fitting inaccuracies, whatever, the center of mass of the disc is slightly shifted from the axis of rotation. Here also the center of mass of the disc, which we call G, is slightly shifted from the axis of rotation, which we call O. So OG is the eccentricity. So E, we denote the eccentricity by E. Now the assumptions are the shaft is massless, or the mass of the shaft is very small compared to the mass of the disc, and the disc is at the midspan of the shaft. Now as the disc starts rotating, what happens? So as the disc starts rotating, so this is the projection in the plane of the disc. So what happens? There is a centrifugal force generated due to this E, and the center of mass being here. So there is a centrifugal force in the plane of the disc. So there is a centrifugal force in the plane of the disc, or there is a centrifugal force in the plane of the disc. In the plane of the disc, there is a centrifugal force in the plane of the disc, which causes the shaft to deform. So here what happens, if you think of the vertical shaft, so this chain thin line is the axis of rotation. This is the axis of rotation. But the shaft has deformed like this, and the shaft and the point on the shaft where the location on the shaft where the disc is mounted is S. So OS is the deformation of the shaft at the location of the disc. So OS is the deformation of the shaft, and SG is the eccentricity. See, when the shaft was not rotating, so S and O were coincident. But as there is an elastic deformation of the shaft which occurs due to the rotation of the disc, this shaft deforms. So the location on the shaft where the disc is mounted, that is shifted from the axis of rotation, which we call small r, and OS is that, and G is the center of mass. So this is what happens in the plane of the disc. So O is the center line, or the O is the axis of rotation. O is the axis of rotation, or the undeformed center line of the shaft, and due to elastic deformation, the shaft has come here at S. So this is S. The shaft has come here at S, and G is the location of the center of mass. So SG is E. So OS, SG, and OS and SG are not coincident. We assume that at time t equal to 0 at time t equal to 0, Sg was like this, and at Sg was like this, so this is E, and at time t, so the rotational speed of the disk being capital omega, so this goes omega t, so this goes omega t. But the elastic deformation of the shaft is something like this, which is also rotating, but we assume it to be lagging behind the unbalance or the eccentricity. So this OS is due to elastic deformation, and this G is the location of the center of mass, which from this line has rotated by capital omega t. So this is what is shown in this figure. And now again this is the figure for the horizontal shaft. So this is the deformed shaft. This is a thin rigid disc, OS SG. This is the undeformed center line of the shaft or axis of rotation. So this is the axis of rotation, or this is the axis of rotation or center line of the undeformed or center line of undeformed shaft. Now this plane actually rotates as the disc rotates. So this plane containing the deformed shaft and the center line, this rotates as the disc rotates. So now you see, suppose this is the shaft, and here there are bearings, and here there are bearings. Suppose we give a force in this direction, then there will be deformation in this direction like this, and if we give a force in the upward direction, there will be deformation like this, and if you divide the force by the deformation, you get the stiffness of the shaft. In this direction, if you divide P by delta, you get the stiffness in this direction, and in this direction, if you divide P by delta, you get the stiffness in this direction. But since the shaft is circular and the bearings are also isotropic, so this stiffness in this direction and stiffness in this direction remains same all the time. So now we are drawing it like this. So that means now the disc is actually supported in two stiffnesses. So these two stiffnesses being equal, and parallel to this stiffness we have taken a damper. This damper is not due to the material damping of the shaft. This is due to some damping that may be present in the bearings. So this C is not due to the material damping of the shaft, but due to some damping present in the bearings. So this K is due to the stiffness of the shaft, and we have assumed two dampings. Now what we do is, so suppose M is the mass of the shaft, mass of the disc. M is mass of the disc, the shaft is massless. M is mass of the disc, and E is the eccentricity. So you can draw it like this: a particle M, a particle of the same mass as the disc at a distance E. So this is the location at the shaft where the disc is mounted. So Sg is E. So actually here to here, instead of showing the whole disk, you are just representing it by a particle of same mass at the center of mass. G is the center of mass. So you can draw this like this: M at E, and the product of ME is called the unbalance. So please remember, the product of ME is called the unbalance. Now we are in a position to actually write down the governing equation. So here you see the disk is, this is where the shaft is fitted, S. So this has shifted X in this direction, this has shifted X in this direction, this has shifted X in this direction, and Y in this direction. So this spring has gone X and this spring has gone Y. So that means here you must get a force Kx, and here also you get a force Ky, and here along with this Kx, due to the damper you get Cx dot, and here due to the damper you get Cy dot, and here there is a deformation X and deformation Y. So this is the center of mass and this is E. So sorry, this is not X and Y. X and Y actually are from here. Let me draw it in some other color. So yes, this is the undeformed center line. So this is X and this is Y. This is X and this is Y. So the force, the disk is subjected to a force Kx due to this deformation of this spring. This has gone a distance X, and this spring has gone a distance Y. So just let me see there. Something like this, and here I will just this is E. So this is omega t. So this is G. So this is X and this is Y. So now if you write down the equations of equilibrium, then equations of dynamic equilibrium, then minus Kx, or the Newton's law you write down. If you write down the Newton's law, so minus Kx minus Cx dot is the force in this direction. This is mass into acceleration, and acceleration is d2 dt2 of x plus e cos omega t, because that is the location of the center of mass. So this is actually the acceleration of the center of mass, acceleration of center of mass in x direction, if you call it x direction. And the other equation is minus ky minus cy dot equal to m d2 dt2 y plus e sin capital omega t. So now if you just take the derivatives and arrange the terms, then you get mx double dot plus cx dot plus kx is equal to me omega square cos omega t, and the other equation is my double dot plus cy dot plus ky is equal to me omega square sin omega t. So if you carefully look, then actually this is the centrifugal force, and this is the x component of the centrifugal force. This is the x component of the centrifugal force, and me omega square sin omega t is the y component of the centrifugal force, if you want to explain that way. So now how is it solved? It is solved like this. So you just multiply this with I, where I is equal to root over minus 1, and you just add the equations. So it becomes mx double dot plus I y double dot plus c x dot plus I y dot plus k x plus I y equal to me omega square e to the power I omega t. So this is the governing equation. Yes, now you call small z as x plus I y. So in vibration problem, actually here also we have taken the force to be something into e to the power I omega t, but there the projection along the imaginary axis is the actual displacement, but here both x and y, the projection along the real and imaginary axis, they are displacements. So that is the difference here. So m z double dot plus c z dot plus k z equal to me omega square e to the power I omega t. And now you take the solution, z equal to capital Z bar e to the power I omega t, where z bar is complex, and replace it here. So you get minus omega square m z bar plus I c omega z bar plus k z bar equal to me omega square, or z bar is equal to me omega square by k minus m omega square plus I c omega. And as this z is complex, it has got both real and imaginary parts, or both amplitude and phase. So the amplitude is me omega square by root over k minus m omega square whole square plus c this is c omega square, and this has got an angle e to the power I phi, where phi is tan inverse c omega by k minus m omega square. So if you take this e to the power I phi in the numerator, so this becomes e to the power minus I phi. So this z bar has an amplitude of this and a phase of minus phi. So this we call z. So this is z into e to the power minus I phi. This we call z. Z is real. So what is the meaning of it? The meaning is what is the solution? The solution is small z, which is capital Z e to the power minus I phi, which is z bar into e to the power I omega t, and z bar is z into e to the power minus I phi. So to the power I omega t. So this is capital Z e to the power I omega t minus. That means this is the amplitude. This is the amplitude of Z. The small z has got an amplitude this, and this is actually lagging the displacement. So here you see, so if this is E, and this is X and this is Y, so this is capital Z and this is lagging behind by an angle phi. So this small z is equal to x plus I y, and its amplitude is capital Z. Its amplitude is capital Z. So here small z is capital Z into cos omega t plus I sin omega t. That means from here you can write that small z equal to capital Z cos omega t minus phi plus I sin omega t minus phi. So from here, so this is capital Z cos omega t minus phi plus I Z sin omega t minus phi. So that means this is actually small x and this is actually small y, and root over x square plus y square, root over x square plus y square is actually capital Z. So capital Z is this much. So capital Z is this much, root over x square plus I square. And if you take projection here, so this angle is, this whole angle is omega t, this whole angle is omega t, so this angle is omega t minus phi, and x is capital Z cos omega t minus phi, and this y is capital Z sin omega t minus phi. So now if you non-dimensionalize, then z equal to me omega square by k minus m omega square whole square plus c omega square. So just like before, you just make it z by e and you divide by k. So this is m omega square by k, and here inside you get 1 minus m by k capital omega square whole square plus c omega by k whole square. And you know what you get? You get this k by m is omega n, that is the natural frequency of the rotor. So this is omega. Omega is the rotational speed of the rotor, and k by m is the square of the natural frequency. So this is square, and this is root over 1 minus omega by omega n square whole square plus, you know, with a little manipulation you can get this as by omega n square. So the if you forget about the damping for a while, then what happens? The highest amplitude occurs when omega by omega n, that is the rotational speed by the natural frequency, is equal to 1. Then the amplitude is highest. And when omega by omega n is 0, z by e is 0, and when it is very high, you can this omega by omega n square. So this is the dominant term. So when it comes out of the root, then it becomes omega by omega n square. So this and these two get cancelled, and you get 1. So when omega by omega n is very large, you are going to 1. So and when the rotational speed is equal to the natural frequency, we call it the critical speed. And this is the angle phi. So angle phi is 0. So you know the expression for angle phi. Angle phi is, if you just non-dimensionalize just like before, so you have got this. So it is twice this omega by omega n 1 minus omega by omega n square. So again you see, when omega by omega n is 0, it's 0. So tan phi 0 means it's 0 degree. And when omega by omega n equal to 1, that is at critical speed, the denominator is 0. So tan phi is infinity. So it goes through 90 degree. And suppose omega by omega n is very large. So this 1 can be neglected compared to this, but the denominator is negative. So this is a negative quantity, and the denominator is much larger compared to this, because this is multiplied by this damping ratio, which is very small. So the denominator is a large negative quantity and the numerator is positive, so it's negative. And the numerator is very small and the denominator is negative, so the quantity is negative, so it's 180 degree. Okay. So now a little bit of explanation. So here we have already drawn this figure. here you see this is for omega by omega n much smaller than 1. Then what happens when omega by omega n much smaller than 1, then phi is very small, and this is omega t. As you know, again you see this is omega t, this is omega t, so this is omega t. Phi is very small, so this and E and OS are, this is OS and E, they are almost in the same line. And what happens when omega equal to omega n, that is at the critical speed, you know phi is 90 degree. So this phi is 90 degree, that means E is here, OS is here, and if you extend, this is 90 degree. So this is like this. And what happens when omega by omega n is much greater than 1, then phi is 180 degree. 180 degree means, so this 90 degree, this has increased, so OS is equal to here and SG is in this direction. They are coincident, but I am drawing it with a little gap so that you can differentiate between these two. So this is OS and this is SG. Now you see, and so when omega by omega n is much larger than 1, Z by E equal to 1 in magnitude and 180 degree in phase. So 1 in magnitude means this OS and GS are same in magnitude. This is Z, so this is S2, this is E, and this is Z. So Z and E are same in magnitude, and E is due to some manufacturing fault or due to some imperfect fitting. So E is expected to be very small. So in that case, Z is also very small. So in supercritical region, this is we call a supercritical because the speed is higher than the critical speed. So this is called supercritical. So in the supercritical region, the OS equal to SG. So OS itself has to be equal to E, and this is also E. So E being small, so OS is also small. So at supercritical speeds, the deformation of rotors or discs are very small, and this we call self-balancing. So this is very important. What happens at omega by omega n much greater than 1? So you see this figure. So Z by E has to be equal to 1 and phi has to be equal to 180 degree. That means, so if this is OS, your SG has to be like this. So since SG is E, OS has also to be equal to E. So E is small, so Z is also, capital Z is also small. So this is called self-balancing. So we stop here, and next we will see one example. We will work out one example.